To quantify and evaluate how effective or move to use a multi-cycle data path over a single cycle data path, we will need to define and use concepts related to performance. We'll start by saying that the most unbiased measure is what we call execution time. Execution time is the time between the start and completion of a task. Say we have a timer, click it when the computer starts running, and then stop our timer when the computer finishes the task or program, then that is the execution time. Aside from execution time, another basis for performance is throughput or bandwidth. Throughput is the measure of the amount of work or tasks done per unit time, which is important in computing systems such as servers. However, we will just focus on execution time. Factors affecting execution time include the design of the machine language instructions. For example, if you have a RISC or CISC instruction set, or aside from the instruction being RISC or CISC, the specific instruction set you're working with. Is it ARM, RISC, MIPS, etc.? Next is the compiler efficiency. The same high-level language program may be compiled into different assembly language programs when using different compilers. Thus, the actual instructions that the processor executes may be different and execution time may be different. Of course, performance is also affected by the hardware you are running your program in. What is the architecture and organization under your computer? What is the implementation technology? 32 nanometers, 22 nanometers, 40 nanometers, etc. Execution time is also called elapsed time and is the total time to execute a program. It is a measure of performance for the whole computer system, including disk and memory accesses, OS overhead, CPU time, and so on. The shorter the execution time, the better the performance. We then define and quantify performance as the reciprocal of execution time. Processor time or CPU time is the amount of time spent executing in the processor. It covers only the period when the processor is actively executing instructions. Since it will be hard for us to determine at this point how long disk accesses are or OS overhead times are, then we will just focus on CPU time and CPU performance. CPU performance is simply the reciprocal of CPU time. CPU time, on the other hand, is a function of the instruction count, the average cycles per instruction, and the clock period. Formula-wise, CPU time is just the instruction count times the average CPI times P. I is in instructions, CPI is in cycles per instruction, and P is in seconds per cycle, and we thus end up with CPU time in seconds. I is determined by the actual program we are running. If we are starting with a high-level program, I will also depend on the target ISA and compiler used. CPI is determined by the CPU hardware. If you have a single-cycle processor, then CPI is 1. For a multi-cycle processor, CPI is something greater than 1. This average CPI is also dependent on the instruction mix of the program. As we have seen in our example multi-cycle data path, instructions may have different clock cycles to finish. Thus, even for the same multi-cycle data path, the average CPI may change depending on the program or instruction mix. Clock period or P is the length of time per clock cycle. If we define R as the clock rate and the inverse of the clock period, then we can write CPU time as I times CPI over R. Since CPU time is in seconds, then CPU performance must be some quantity per second. Also, the larger the CPU performance or the shorter the CPU time, the better. Speedup is used to compare the performance of two systems. It is defined as the ratio of performances, but since we are dealing only with CPU performance, then we'll use the ratio of CPU performances instead. Note the denominator is the base or reference performance. Since CPU performance is the reciprocal of CPU time, then speedup can also be written in terms of CPU time, but this time we need to put the base or reference CPU time in the numerator. Based on the formulas, we can say that the new CPU or system performs better than the base or reference CPU or system if the speedup is greater than 1, worse when the speedup is less than 1, and has the same performance when the speedup is exactly 1. There are different ways in which we can phrase or compare the performance of two systems in sentences. For example, A is 2 times faster than B is the same as B is 0.5 times as fast as A, CPU time of B is twice that of A, or the speedup is 2 from B to A. Let's look at some performance and speedup computation examples. Consider a sorting program with the same input set condition that was run on 4 different computers. Computer 1 finished executing the sorting program in 1.6 seconds, while Computer 2 finished it in 3 seconds. Computer 3 was said to be 0.8 times as fast as Computer 2. Computer 1 was said to be 1.5 times slower than Computer 4. We are then asked the following: How much is Computer 1 faster than Computer 2? How long did Computer 3 execute the sorting program? And how long did Computer 4 execute the sorting program? To summarize, we are already given the execution times for computers 1 and 2. Let T represent the execution time in seconds. It was also said that Computer 3 was 0.8 times as fast as Computer 2, and thus the speedup from 2 to 3 is 0.8. The last statement in the given can be reversed, and we can say that Computer 4 is 1.5 times faster than Computer 1. In this reversed statement, the reference becomes Computer 1. Thus, the speedup from 1 to 4 is 1.5. To guide us in our solution, we provide here a summary of the given at the side. We also provide the formulas for our reference. The first question asks us to get the speedup between computers 1 and 2 with computer 2 as the reference. Thus, the speedup of 1 relative to 2, or from 2 to 1, is the ratio of T2 and T1. Computing 3 over 1.6 will give us the answer 1.875. For the second question, we will use the given speedup from 2 to 3. The speedup for computer 3 relative to 2, or from 2 to 3, is 0.8. So, 0.8 is the ratio of T2 and T3. Solving for T3, we have T2 over the speedup, or 3 over 0.8, and we get 3.75 seconds. For the third question, we can use the same approach to solve T4. We note that the speedup from 1 to 4, or 4 relative to 1, is 1.5 and is the ratio of T1 to T4. Thus, the execution time for T4 is simply T1 over 1.5, or 1.6 over 1.5, which gives us 1.07 seconds for T4, and thus we have already answered all of the questions for this first example. For our second and last example for this lecture, an assembly program was first ran as a single-cycle processor with a clock speed of 100 MHz and had a CPU time of 4 milliseconds. The same assembly program was then ran at 650 MHz multi-cycle processor with the CPI for different instruction types as shown. It is known that the program executes 100,000 load words. For the questions, we have: how many instructions are executed for the program to finish? What is the effective CPI for the multi-cycle processor for this problem? What is the CPU time for the multi-cycle processor? And what is the speed up from the single to the multi-cycle processor? The key information from the given is written below. We are given the clock rate for the two processors the CPU time for the single cycle, and that the program executes 100,000 load words. For the first question, how many instructions are executed for the program to finish? We can start with the single cycle processor as we know the CPU time for it. Note that for a single cycle processor, each instruction takes 1 clock cycle to finish, so the CPI must be 1. The formula for CPU time is I times CPI times P, or I times CPI over R. Thus, 4 milliseconds is equal to I times 1 cycle per instruction times 1 over 100 times 10 to the 6 seconds per cycle. The instruction count I can then be computed as 4 times 10 to the minus 3 times 100 times 10 to the 6 over 1, which gives us 400,000 instructions. For the next question, what is the effective CPI for the multi-cycle processor? We use the most recent information that we have 400,000 instructions. From the given, it is said that we have 100,000 load words, and thus the remaining non-load word instructions must be 300,000. From the table given, the CPI for load word is 5, while the CPI for other instructions is 4. The program is made up of 25% load words and 75% non-load words. Thus, the average CPI for this program, for this multi-cycle processor, is 5 times 25% plus 4 times 75%, and evaluating this gives us 4.25 cycles per instruction as the average CPI for the multi-cycle processor. For the third question, the CPU time for the multi-cycle processor is asked. CPU time again is I times CPI times P. For the multi-cycle processor, this is 400,000 instructions times 4.25 cycles per instruction times 1 over 650 MHz. Evaluating this gives us 2.615 milliseconds. For the last question, what is the speed up from the single to the multi-cycle processor? We can set up the speed up equation with the single cycle processor as the base or reference. The speed up then is the CPU time of the single cycle processor over the CPU time of the multi-cycle processor. From the given, the CPU time for the single cycle processor is 4 milliseconds, while the CPU time for the multi-cycle processor is 2.615 milliseconds as computed above. The speed up therefore is 1.53 unitless. Thus, we can say that the multi-cycle processor in this example executes the sorting program 1.53 times faster than the single cycle processor. We end this lecture by recalling the concepts introduced regarding performance. First, performance is the reciprocal of the execution time. CPU performance is the reciprocal of CPU time. CPU performance can be computed as R over I times CPI, since CPU time is I times CPI over R. Next, the instruction mix as dictated by the program considered and the per instruction CPI as dictated by the processor implementation affects the average or effective CPI. We can improve performance by using a faster clock. This always improves the performance, although note that processors have a maximum clock speed at which it can run reliably. Thus, we can also use a faster version of the processor or hardware that can support a faster clock. We can also shift to a different ISA. Here we know that there is a trade-off between I and CPI and/or R. CISC programs may be shorter and thus have smaller I, but may have larger CPIs or slower clocks. We can therefore not generalize or say that RISC processors will always perform better. We still need details regarding both hardware and software. We can also consider changing the compiler. A different compiler can result in a different assembly program. Thus, the number of instructions may change. The compiling can also result in a different instruction mix and influence the average CPI. We can also consider more advanced techniques such as pipelining, superscalar operation, multi-core or multiprocessors, or even use a multi-computer approach. Superscalar execution is where we issue two or more instructions at the same time. To do this, we need to have multiple copies or enable multiple accesses to the main data path blocks. Multicores or multiprocessors make use of separate data paths to execute different portions of the program in parallel. Multicomputers use physically separate computers that can be thought of to work independently but performing different tasks at the same time. One common example is when multiple servers cater to or service requests to a website with a very high demand or usage. Pipelining is a technique that involves instruction-level parallelism. We will discuss pipelining in the next lecture. And that's it for this module. Thank you very much.